I'm Kuan-man. When I came here to UCLA, I didn't have much trouble to choose my research topic, so I was interested in Q optimization and convections. So at that time, Steve Kruger just finished it, and he was ready to take a faculty position in Utah. So he helped me study, so it was pretty easy topics, and finished my degree and went to Colorado State University with Dave Landau, and then I moved to NASA Langley because they have a lot of satellite data available, so I take advantage of those data products and do some satellite data analysis. So in this talk, I mainly look at the sensitivity of in-cloud properties and relative flux to the degree of convective aggregations. So in the last 2 days, we have several speakers talking about convective aggregations. And I acknowledge the support from the NASA Science of Terra Aqua MPP programs, and also with help Yaping Zhou and Menggu Sun. So just give you a very brief introduction about convective aggregations. So it's a phenomenon produced by cloud design model, also general circulation model. It's under uniform sea surface temperature, so you run the model under relative convective equilibrium, and you run for for quite a few, for about 50 days, and convection can organize in a single big block. So those plots showing the show the water vapor and precipitation and surface flux. So it doesn't show in the cloud properties inside simulations. So what I'm interested in looking at the less aggressive state, like day 10 versus day 50, so to see how this in-cloud property change between two states. So basically use two different products. One called single scanner footprint. That's from a series project on the Aqua satellites. And that product I basically use to produce something called cloud objects. So you select some region with the same properties. So the shaping size determined by the satellite footprint data and the selection criteria. So for this study, I'm only interested in the deep convex clouds. So we use the cloud up depth greater than 10 and cloud top temp height greater than 10 kilometers in overcast conditions. So basically, those select convex tower and the very thick annular clouds. So when those footprints are connected together, we select one cloud. And in this study, because we don't want to select all those single point footprint as a cloud object, so we make a decision, only select those over 75 kilometer size. And in this study, we also use cloud type, flux by cloud type products, which is based on the pixel level. That's pixel size is 2 by 2 kilometer squares, and footprint is 20 by 20 kilometer squares. So over 10 by 10 grid box, we're using the pixel data to produce the escape diagrams, the International Satellite Clouds Climatology Program. So it's 6 cloud up depths, being and 7 cloud pressure beings. And so we have 42 cloud types, and we only select those 10 by 10 grid box with at least one cloud object in the grid diameter grid than 75 kilometers. That means about 12 grid footprint. So here showing some examples, and on the top of each plot, I have some of those numbers. I discussed those aggregation index later, but you can see as number of cloud object increases, those numbers change, and basically that's the number of cloud object is a pretty good indicator how to convective aggregate. So additional constraint we use is we only look at the oceanic areas, and this plot I show in the PDF of the omega 500. So we cut off the tail, anything omega absolute value greater than 0.1 excluded. And we also looked at different precision regimes. So we divide the data into 5 different equal bin sizes. So choose the second and fourth bins. And the other information I sent there is the number of samples. You see from the unique n equal 1 have almost 24,000 samples, and then you with 2 cloud objects, you reduce by half, and 3 objects, another half, and the last one less than half, because I also have those objects have more than 4 cloud objects, 5, 6, 7, 8. So you can see the sample size decrease as number of cloud objects increase in the object, in the gray box. And those have 4-year data set, and the Maya tool analysis used for omega and persistence. So this is the first result I'm showing. It's deviation from the entire data set, and this is for the cloud fraction areas. So it's basically like frequency occurrence for each cloud type minus the sample means. In the sample mean, those values could be, the maximum value is about 10% for some annual cloud type. So those are in the top, in this cloud type, and near the surface, the mean data sample only have maybe 4 or 5%. So the change, the deviation look pretty big, and this is showing the number of objects from 1, 2, 3, 4 for the second precipitation regimes, and the bottom row is for the fourth precipitation regimes. You see some difference between those 2 precipitation regimes, but for both regimes, the upper level and middle level clouds increase as the number of cloud objects increase. That's mainly because all those connected anvil have much larger area compared to a single convector towers. And you look the difference between those 2 precision regimes. For n equal 1 and 2, there's more difference. But overall trend is the same. And the other feature there is the low clouds decrease as number of objects decrease. So that's a little bit similar to what cloud result model produce when convection is more organized, aggressive. So now I'm showing the difference between 1 cloud object minus those grid with 3 cloud objects. That's on the top rows for second, fourth, and all precipitation regimes. And the bottom showing those with 2 cloud objects minus 4 plus objects. So if you don't look carefully, each of the panel looks identical. But I assure you, I didn't make a mistake plot this diagram because I did it myself. So you can see so when convection is more aggregated, so there's fewer cloud objects inside box, the upper level and the high-level angular clouds is less, but the shallow cloud is a little bit more than for less aggregate cases. So this basically means the number of cloud objects could be a good indicate to measure the convex aggregations. But I've shown other difference there that shows the long wave radial flux. And you see those impact by both the moisture profiles. So when convection is more aggregate, so one or two, one unique cloud object, you have more long wave emissions for the upper thin clouds, and also for the lower clouds. So those results indicate, you don't need to separate into different regimes to look the differences. And now I describe those convex aggregation index. There's 3 of them. The first one was proposed by Tobin et al. In 2012, called simple convex aggregation index. So basically, it's a normalized number of cloud objects times the normalized distance between object versus domain size. So the second index called convective organization potential. It's basically the ratio between the sum of the radial radians divided by their distance. So you have all those pair of cloud objects together and add them together. So in this definition, the number of objects is not explicit in the definitions, but in the first definition it does. And the third one, similar to the first one, I call the MCAI. So the modification was the distance. So instead of choose the distance between the central, between the two objects, we choose the edge. So how close those two objects are next to each other. So this is showing the scattering diagram with different density. So you can see the SCAI, the first index, and versus the MCAI is pretty much linear, and most of them are here. And modified one can reach all the way to 0, but the SCAI is always greater than 0. And you notice the convex organization potential are very closely related to the modified one than the original ones. So basically, I divide the data sample into 3 equal size. So only compare the stronger aggregation samples versus the weak ones. And so another point I want to make is for the weak aggregation cases, it's very scattered in those 2 index versus the convex organization potentials. So this is results showing for the cloud area fractions between the strong aggregation index subset versus the weak ones, and for those 3 index. So if you remember the results showing earlier for the number of cloud objects, this panel is almost identical. The middle clouds and the upper level clouds, angular cloud reduce as convection become more aggregated, and the shallow clouds is doing opposite. But for the convex organization potential, those upper thick clouds, so the upper depth is very big, they are much more frequent compared to the other index. And the lower panel just showing the liquid phase clouds. And this is showing compared the long wave, and the bottom panel showing the albedos. So you convert the albedo to short wave, is about same order of magnitude. You see there's more difference in the upper thick ambient cloud areas. So the last result I'm going to show is compare the partial derivative of the mean values. So I decompose in the change due to cloud fraction and change due to properties. And this is expressed as the difference from the environment. So it's more like cloud-related effect. And this term is much bigger than the second term. And the last one is have some contribution for long waves. So this is showing the last result. It's showing the total change due to the cloud area fraction change. And you see those three index results are quite different, but you notice the long wave, short wave almost totally cancel each other, except the low-level clouds, those low clouds. So here's my conclusions. So I take advantage of those two series high-resolution data products. One footprint data is 20 by 20 kilometers square, and the flux by cloud type is 2 by 2 kilometers squares, and studied that based on the escape diagrams. And the first conclusion is similar to what Toby 2012 and 13, but they use the domain average properties to compare the sensitivities. So there's some consistent there, but from the other index, you can see there's some difference, especially the convex organization potential behave very different from the original index. And the modified one is somewhere in the middle. And the other thing I noticed is the total long wave, short wave change due to cloud fraction change are very large compared to the in-cloud property change. And those two changes cancel each other. And of course, there's a lot of limitations. One of them is I wish they have the surface long wave, short wave flux, so I can look the column atmosphere heatings. But that's not easy to produce. That's it.